So last class we looked at this function g that's defined as an integral. And we talked about how it's kind of an area finder, where we're finding the area under f from a to whatever the input of the function g is. And as a calculus student, since we spent most of the fall calculating derivatives and finding derivative rules, I think a natural question to ask is, if I'm presented with this new function g, what's its derivative? Right? Because derivatives tell me lots of things about the function g. When does g increase and decrease? When is g concave up and concave down, etc., etc.? So that's a good question to be asking. So when we have no idea what the derivative rule is, we have to go back to the definition. So by definition, g prime of x is equal to the limit as h goes to 0 of g of x plus h minus g of x over h. Now we need to make sense of what these symbols are and see if we can come up with something for this expression g primed. So we take a limit as h goes to 0 of this expression. Now what is g of x plus h interpreted as? Okay, g of x plus h would be what I would get if I plugged in x plus h everywhere I saw an x into function g. So g is this integral function, so g of x plus h would be the integral from a to x plus h of f of t dt. So far so good. G of x is explicitly defined as the integral from a to x of f of t dt. And this is all divided by h. Now, let's take a look at what these integrals are talking about in terms of area. This first one is the area under f from a to x plus h. So that's starting here and ending at x plus h, which is somewhere to the right of x, if we assume that h is positive. So that's finding this area here in blue. Now, we're subtracting the integral from a to x of f of t dt. So that would take away the area from a to x. So I'm going to erase that, and this little strip here is what I'm left with. And there's another way to rewrite that. Instead of saying that difference I have in the numerator, I can rewrite that as what? The integral starting at x and ending at x plus h of f of t dt. Okay, so we're still dividing by h. We're still taking a limit as h goes to 0. Now, what we're going to do, since we want h to be pretty small here, means this little gap here between x and x plus h is going to be tiny, I'm going to zoom in and see what this function starts to look like. Okay, and this is going to help us evaluate, or at least get an idea of how to evaluate this limit right here. So if I zoom in on that region, I know that the curve is going to look like a line, and what that means is that region from x to x plus h looks like a trapezoid. Okay, so let's remember what we're doing here. We're doing g prime of x is equal to the limit as h goes to 0 of the integral from x to x plus h, that's that yellow strip over there, of f of t dt. And all that's still divided by h. So this integral is basically saying find the area of that region and then divide it by h. When we zoom in, that region is a trapezoid. And I know how to find the area of a trapezoid. So I'm going to replace that integral in the numerator with the area of a trapezoid and then divide by h and see if that helps me in my calculation here. Okay, so what is the area of a trapezoid? Well, it's going to be 1/2 times the altitude, or the base, or the height, I guess is what you call it. This is going to be right here, the altitude, this distance. So if we do x plus h, comma 0 minus x comma 0, we'll be left with h is the altitude of the trapezoid. And then we take that times the sum of the two bases. Okay, now the two bases are these two vertical strips here. If this is x comma 0, then up here is x comma f of x. And the second base will be determined by the coordinates x plus h, comma, f of x plus h. So the first base is the distance from x f of x down to x comma 0. That distance is simply f of x. The second base is determined by the distance from x plus h, comma, f of x plus h down to x plus h, comma 0. And that distance is simply f of x plus h. So now we're getting somewhere. Okay, I've replaced that nasty integral with a easy trapezoidal area calculation, because when we zoom in on a curve it looks like a line. And now I can do some simplifying, because there is an h in numerator and denominator, and that would leave me with this limit here. The limit as h goes to 0 of 1/2 f of x plus f of x plus h. If I substitute 0 in for h, I get 1/2 times 2 f of x's, because f of x plus h approaches f of x when h is close to 0. The 1/2 and the 2 cancel, and I'm left with f of x. So the moral of the story here is that the derivative of that function g is actually f, the function that we're finding the area under. Okay, so here's it stated formally for you, and this is big. Okay, it says the derivative of this function, this is an integral function, ends up being the integrand, sort of. Okay, here's what it says in English. The derivative of an integral function is the integrand, that's this, right, as a function of the upper limit. Here the upper limit is x. So notice that we ended up with f of x, not f of t. This is part 1 of what's called the fundamental theorem of calculus. It's a big deal. Okay, this tells us how to take the derivative of an integral function, and the way you do that is by noticing that basically the derivative and the integral sign wipe each other out. Let's do a couple quick examples. So we've seen that these three functions here could be area finders, and we can now calculate the derivative of the area finders and do all sorts of analysis. Fundamental theorem says the derivative of an integral function is the integrand here is t squared, as a function of the upper limit. So instead of t squared, the integrand becomes x squared. The derivative and the integral sign wipe each other out, but I must be in the same variable that I'm taking the derivative of, which is x. Second example, the derivative of the integral from a to x of e to the sine t dt is equal to the integrand as a function of the upper limit. So it's going to become e to the sine x. Finally, the derivative of this. Now this is not quite an integral function because what? The x is in the wrong place, right? The x should be the upper limit. So let's just make a small adjustment. Plug a negative sign out in front using that property of integrals that I know. Go from 2 to x. Everything else stays the same. And now I can apply part 1 of the fundamental theorem. The derivative of the integral function, that negative side is going to come along for the ride, is equal to the integrand sine of ln of x, not of t, okay, because that has to be a function of the upper limit. Now, you say, part 1 of the fundamental theorem? I say yes, because there's 2 parts, because we don't have to stop there. If we know that the derivative of this function is this, well, maybe we have a way to determine what this integral is equal to without having to do Riemann sums and all those nasty limits that we don't want to have to calculate by hand. So how do I undo a derivative? Well, if I undo a derivative on the left side, I'll be left with the integral of a to x of f of t dt, which is an expression I don't really know how to evaluate very easily. Now, if I undo a derivative on the left, I have to undo it on the right, and that process is called taking an antiderivative. An antiderivative. We have a symbol for antiderivative. In this case, it'd be capital F of x. And since there are many antiderivatives, we have to add a constant. Now, we want to solve for this constant because otherwise there are many answers that could work here. So is there a value of this function on the left here that we know the value of for certain? And the answer is yes. Okay. If we let x equal a, that's the one value we know for certain because the integral from a to a of anything is always 0. If we substitute a in, we're going to get 0 is equal to capital F at a, that's the antiderivative of f at a, plus a constant, and therefore we can solve for the constant, which becomes the negative antiderivative of f at a. This is a number. So now we can go back up to this line here, so, substitute for the c. So now we'll have integral a to x, lowercase f, is equal to capital F of x minus capital F of a. And if now we want to do a definite integral, which we're mostly concerned with because we're doing areas, so let's let x equal a number, let's call it b, then we have a way to evaluate definite integrals without doing sigmas and limits. Okay, here's how it works. The integral a to b of f of t dt, or f of x dx, is equal to capital F of b minus capital F of a. So in English that says this: the definite integral from a to b of f is equal to the difference between the antiderivative of f, that's capital F, evaluated at the two endpoints. This is part 2 of the fundamental theorem of calculus, which we abbreviate with FTC. Let's do a couple quick examples. These were all thought of as area calculations when we first were introduced to the integral, and they still are. But now we have a new way of calculating them without doing rectangles and Riemann sums, sigmas, and limits. The fundamental theorem part 2 says, take any antiderivative of x cubed, okay? Since I can take any antiderivative I want, I'll take the easiest one where the c is equal to 0, okay? 1/4 x to the 4th, and then we need to evaluate this at the two endpoints and subtract, okay? Mathematically, this is the convention for writing the work. We write the antiderivative. If you want to write a plus c, that's okay. You'll see what happens to it. And then we put a bar, a vertical bar, which means such that we put the lower limit on the bottom and we put the upper limit on the top. And then we plug in first the upper limit. So we would get 1/4, 3 to the 4th. And then we subtract 1/4 times 1 to the 4th. So what I've done here is this is big F of B minus big F of A. So I'm executing the operations of the fundamental theorem. Okay, what do we got here? 3 to the 4th is 81, so I have 81/4 minus 1/4, which will give me 80/4 or 20. And if you remember last class, we actually did this calculation on the calculator with sigma, and we got 20 as an answer. So the actual area done by hand now, underneath the curve x cubed from 1 to 3 is 20 units. Okay, and there's a picture of it right there. Okay, let's do the area underneath the curve sine x from 0 to pi. Fundamental theorem says you can do this by hand. Find an antiderivative for sine x. Antiderivative for sine x is negative cosine x. And I'll go ahead and put a plus c so you see what happens to the constant, because you just need an antiderivative, any one you want. We put a such that bar, we put a 0, we put a pi, and then we subtract. Okay, so we have to do negative cosine of pi plus c. Now be careful with your subtraction here. Minus negative cosine of 0 plus c. Now let's evaluate. The cosine of pi is -1, so the negative cancels, and we have a 1. 1 plus c minus the negative cosine of 0. Cosine of 0 is 1, so I have a -1, and we're subtracting, so it becomes a +1. And we're subtracting a c. So the c's cancel out, and they always will, so we might as well not write them. in this situation because they always wipe each other out. And so we get an answer of 2. So here's a picture of what we found. We're finding the area underneath the curve sine x from 0 to pi. And we got 2. If you remember, we did a simulation last class where we did 1,000 rectangles, and we were watching what the area was adding up to. It was very close to 2 units. Let's do one more. Same function, but this time we're going to go from 0 to 2 pi. So again, we need an antiderivative for sine x. So I'll use negative cosine x such that we're going to plug in these two numbers. It's like a reminder. So I do negative cosine 2 pi minus a negative, so I'll make that a positive, plus the cosine of 0. Negative cosine of 2 pi is negative 1 plus the cosine of 0, which is 1, so I get an answer of 0. So this is telling me the area between the curve sine x from 0 to 2 pi is equal to 0. Here's a picture. And so we see that that's not exactly true, but remember the integral represents signed area. So this area here, which the integral calculates as positive, actually cancels out this area here, which the integral calculates as negative. So the integral comes out to be 0. If I was actually talking about area, I'd say the area was 4, 2 here and 2 here. But since we're doing an integral, we know the integrals can have negative values because of the signed area concept.